name is Martyn Pemble and I'm the head of the Advanced Materials and Surfaces Group here at the Tyndall National Institute, University College Cork. One of the things that my group is involved in is the method known as atomic layer deposition, or ALD. So ALD is an extremely versatile technique for the deposition of ultra-thin layers of materials, and the advantage of ALD is that it can be used to grow materials at a rate which is literally equal to around 1 atomic layer per cycle. And here a cycle can last anywhere between a few seconds and maybe a minute or so. So typically we're able to deposit layers of materials such as metal oxides, and here we're thinking of materials like aluminium oxide, hafnium dioxide, zirconium oxide, titania, and materials of this sort. But we're also able to deposit other materials such as metals, metal nitrides, and even sulfides can be deposited using atomic layer deposition. So in ALD the growth rate is typically very slow, as I've said, around about 0.1 nanometers per cycle. But this of course comes with an advantage in that associated with the slow growth rate is the ability to coat complicated surfaces extremely conformally. My group is involved in a number of different application areas, including the growth of high-K dielectric layers for advanced CMOS processing, the growth of metals by ALD for back-end interconnect applications, and also we're involved in other areas which are becoming increasingly popular applications for atomic layer deposition, which include the use in solar cells and photovoltaic devices, MEMS systems, and even medical devices can benefit from the deposition of coatings by atomic layer deposition. The last application that we're familiar with is simply the growth of metal oxides to act as moisture or oxygen permeation barriers. So as well as being involved in a number of research projects, our group is also part of a strategic business unit here at Tyndall, which is called ALD Technologies. What we aim to do here is to provide a service in the form of custom growth and consultancy in the area of atomic layer deposition, but also supply to those customers who want them very small, dedicated experimental ALD reactors which have been designed with the experimentalist in mind.
My name is Nolan. I'm a researcher here at the Tyndall National Institute investigating the deposition of metal and metal oxide films by atomic layer deposition. One of my most recent projects is with the European Space Agency, depositing iridium X-ray reflecting films into high aspect ratio substrates for their silicon pore optic program. To enable me to study the influence of various reactor conditions on the films deposited, I designed and constructed the reactor you see here. As part of the initial commissioning trials in the reactor, aluminium oxide films were deposited into both high aspect ratio glass tubes and flat silicon wafers to enable me to study the influence of both reactor temperature and precursor pulse and purge times on the characteristics of the films. In a typical film deposition, the surface to be coated is exposed to the chemical precursors in a sequential fashion to form a continuous film. If we take the deposition of aluminium oxide as an example, a pulse of trimethyl aluminium enters the reactor over a heated substrate where it reacts with hydroxyl groups on the surface that have formed through the absorption of water present in the air. Methane is the byproduct of this reaction, which terminates when all of the available hydroxyl groups on the substrate surface have been exhausted. A purge cycle is then introduced to remove the methane byproduct and any unreacted trimethyl aluminium. Following the purge cycle, water is pulsed, which reacts with the surface methyl groups to form oxygen bridges between the aluminium atoms, leaving a hydroxyl group on the surface that can react with a subsequent trimethyl aluminium pulse. Unreacted water and methane byproducts are removed during another purge cycle. Successive precursor pulse and purge cycles deposit a monolayer of aluminium oxide each time, leading to a uniform conformal coating on the substrate.